Mr. Cornwall is coming. Everybody clap. I only have to stall for a few minutes. And if Peter is ready, did you want to say something? No. Okay.
Yeah. Want to say a few words for my sake?
You need another minute?
No.
Okay.
Finishing time, Peter? I can go back up and back.
No.
Okay.
You're here now.
All right.
I can finish this.
So we're going to start with Peter. He's going to talk about the machine that he dreamed up, and he's going to show us what of it is working and what isn't, and explain how it will work. Okay?
Yes, sir.
You know, in comedy, they say to lead with your second best joke and end with your best one. That's not happening today, right? But my name is Peter Elitis, and I am here to present to you my project, my painter bot graffiti machine. Yeah, let me take that. My name is Peter Elitis, and I'm here to present to you my painter bot graffiti machine, or the design of it. Right. Am I not in the presentation mode? Here we go. Graffiti is an art style that I like a lot. It's like, it's with the really bold colors, the blocky lettering. I think it's like just visually very interesting. It's a very unique art style that I really appreciate. So I wanted to do something with that this year, or the last semester and a half. And I came up with this goal. I want to build a robot that takes the artwork that I give it to it, artwork that I design in Fusion 360, a CAD program, and export that as CNCG code and have it do something that will put it on a piece of paper or a wall or whatever I decide. So I did a lot of research on graffiti machines beforehand, and something kind of similar to this project that I found was this Graphomat machine, as you can see up here on the right, designed by artist Nicholas Roy. But I found one kind of main problem with that, and it uses this gantry design. You see a lot of 3D printers if you've ever seen one of those. It's not really easily like scalable without me going back and getting like a new frame built and like changing the code a bunch. So I wanted to go for something that I could theoretically put in 2 separate corners and change the code in very minor ways and have it kind of work on whatever scale that I give it. So I came up with this initial design. I want to take, like I said before, I want to take my some G code that I make on a computer and put it into my main system, this main microcontroller. We're using a Freedom board, KL25C. I want to use spray paint cans. I picked these Montana Gold colors, and I'm designing everything around that. I want to take that G code that I give it, and I want to have it move this V plotter design that I came up with, which basically uses 2 motors in the corner, and that kind of drives, oh yes, I forgot about these. It drives this, It drives this paint module in the middle. Let me use this other one. And the paint module doesn't communicate to the system in any like wired context. It's not wired to this kind of main microcontroller that's controlling everything. I want to send information to this wirelessly to tell it to either spray or not spray, essentially. And one more thing I wanted to mention is it uses these counterweights to balance it out and keep it where I want it. So before I go into like the real like nitty-gritty of my design, I wanted to outline kind of how I wanted to make a piece of artwork with this machine, because that's my end goal. I want to design something in CAD and then make it do that, essentially. So I want to start with the color blocking, just like the basic shapes of everything. I want to then blend the seams between those two colors. You can see that kind of at the top, in between the red and magenta. It kind of blends together instead of being a high contrast kind of line. I want to go, then I want to do details. If you look back up, I want to put the smiley face over everything. I want to do like stripes and dots and whatever I can dream of, really. And then I go through, I do those black outlines, and then go through and highlight and low light everything with white or whatever color. But that's basically like, that's what I want to accomplish through this machine. So real quick, now that we're going to get into the kind of nitty-gritty design, I want to go through the paint module, the kind of main interesting bit about this machine. I did a bunch of testing beforehand. I got the dimensions of the can. I got how much it takes, like how much force it takes to actually spray this can. And I threw up my design goals, my wireless communication. I'm going to use an Arduino Nano that will be hooked up to the kind of wireless receiver, and it'll be interpreting the data that's sent to it. And I'm going to power it using a battery. Here's more on that CAD model you saw on the last page. I have these kind of pins and C-clamp system to hold everything together. And it uses this cam design you can see in the section view. And it's hooked up kind of using these arms and linkages, this 4-arm linkage connected to that servo motor. So when the servo motor moves, that cam will move and actuate the cam. So for wireless communication, what I decided to do was use these little 315 megahertz wireless kind of receiver transmitter modules. And they're 315 megahertz because that's like an FCC registered frequency that people are allowed to use and make things for. They're wired, like I said, to separate microcontrollers, separate computers. One is the KL25C that runs the main machine, and the other is the Arduino Nano that I outlined in that slide. And it sends information as a kind of square wave that I'm going to talk about a little bit more, I think, with the next few slides. So yeah, that square wave is going to send just this constant kind of on and off signal. And my goal is to change how long that signal is on for using pulse width modulation and read that kind of percentage time, that the duty cycle as it's called, to change the state of that servo motor and to actuate the can. And on the right here, I put up some code. This is test code for the KL25Z, and it allows me to set the duty cycle to the 5 and 10%. And this is an oscilloscope output of the yellow being the transmitted signal and the blue being the received signal. So going over, once that data is sent, we're in our kind of Arduino space now. And this is the code that I developed to measure the duty cycle that I kind of mentioned before. And it's going to do something. In this case, it's going to be moving that servo motor and actuating my paint. So for starters, I just kind of initialize all my variables. It's very simple. But then I go through and build this function. I take the on time that the pulse is on and time that it's off, and then take the percentage that it's on for, and that's my duty cycle. The frequency calculation I do is just to, it was for debugging, it doesn't really need to be there. And then up here, I'm just checking what the duty cycle is. If it's within plus or minus a half a percentage, I'm going to say that's close enough, it's 50, or close enough, it's 10, or whatever. And then it's going to change the state to, this is 180 degrees of 0 degrees. It's going to go kind of make a half circle. Next, I want to go over my design for the motors and belt system. This part kind of took the longest and is one of the more intensive parts of the system. The motors, I work a lot with 3D printers, and they use stepper motors a lot, and I wanted to learn how to use them, so I selected a high torque stepper motor called the NEMA 23. Produces 8 kg/cm of torque. And right on the screen you can see I have this little drawing set up of how I intend to build the motor assembly with the timing gear, the pulley that I mentioned here, with a belt running over it, and this little spring slip prevention system to stop the belt from coming off. This is the wiring, it's the electrical side of the stepper motor. I use this little A4988 motor controller, which basically allows me to use the KL25Z controller to send signals to it and control how many steps the motor goes. So you can see each motor has two coils, and I connect 2 of them, two sets of pins into another set of pins, and then that's what allows me to code in the KL25Z and get an output from those motors. I'm going to take the next 5 slides to go over my math. It's really simple, but I just wanted to outline kind of how I'm giving it coordinates and expecting it to give me something reasonable back. So that red dot is kind of our desired coordinate positions. And then basically from there, I draw those 2 triangles out where their hypotenuses are A and B. I take the height of we keep in mind the height of the machine and the system, and then the width of it as well. I can get those two lengths and then get the belt lengths using some math that I have right here, where our kind of x1 is that you go from the center point for the x, and then you add your the kind of desired x to it, or you add you subtract the y because the system, this right here would be your midpoint. So if I wanted to go up, I'd subtract y in the case of the code. And then we assume that it starts in the center. And just to get the belt lengths, we just call on our good friend Pythagoras. I think we all know him, and just do and get those hypotheses. So here I've done the same thing. I've shown the same slide. I just input numbers, and I did some really simple ones just to show what I'm doing. I put 50 millimeter, kind of just a straight slope of 1 line, and I made the width and the height the same. I made a square a meter by a meter, and then I do all that math out, and we get our kind of desired lengths. But the goal is not just to have the lengths of the belt. We need like a number of steps that I can actually give to those motors and produce like some actual motion with. So to go from belt length to the number of steps in the motor, this is just some basic gear math. I've been working a lot with gears recently, so it was kind of relatively simple. You have this kind of number called the module, which is the belt is moving along this kind of circle, and that kind of pitch diameter, that pitch circle as we call it, it is like the circle the belt is actually moving along. So I take that module, which is like, that represents kind of our pitch, and then we take the number of teeth, which gives us the diameter of that circle, and then we multiply by pi to get the circumference. And then from there, we divide our circumference by 200, because the motors that I'm using have 200 steps per revolution. And then to get the steps actually required, we take that belt length, divide it by the distance that the motor travels, or the circle travels per step, and we have the number of steps I need to input into those to actually get a actually get the belt to move where I want it to. So again, I put in all my numbers, and I'm using those same example numbers, that 777 and that 710 from motors 1 and 2, and it outputs like near 1,300 steps to go 1, to do for the first motor, and then for the second motor, it's almost 1,200. And here's the math. I put that math into some C code and kind of had it do it out, so just to check my work, and I get the same results. And why did I just spend the last 5 slides talking about all this math that we don't care about? It's because I care about it, and it's important to give those motors the numbers. And this code I'm showing on the right actually manipulates them. There's 3 main things I have written in that code. It's my position reference, my step count, and my error. So you can see there, it's checking. It does the math out. It takes the error. The step count is the number of steps that the motor has currently moved, and the position reference is where we want it to go. So the position reference is what we did all that math to get. So we input that, whatever number we want, into the position reference, and it subtracts the step count from that, gets the error, and then has the motor move that many steps to go where I want it to go. And this is a quick demo of that working. I made it do a little test pattern. I gave it 4, 5 coordinates, and this is it drawing a little square where it goes out from the center, draws my square, and then returns to the center. So I'm going to play that now if this is going to work. Am I going to play it? Technical difficulties, folks. I can play that. But here you can see I press start, and it goes out, it draws my little clockwise square. I want to talk about that specific kind of bow outward in a minute. But yeah, I gave it 5 sets of coordinates, goes out, draws a square, comes back. So, real quick, the one thing that came up when kind of looking into the B-plotter method as opposed to the kind of gantry system that I went over earlier, it's a lot more scalable, but I need a lot more control over the motors to actually to get straight lines and kind of diagonal lines out of them. Because if I don't separately control the speeds of the motors, I get what's called in like CNC machines the dog leg effect. And that's basically where one motor is going, it's going from point A there. You can see it, and then one motor stops. So then the other motor is still going, and it's dragging it the rest of the way. So you get this kind of bow effect. And you can see kind of in the screen cap from my demo that I just showed you, it's doing that. One motor goes in a diagonal for a little bit, and the other motor pulls it to the end. And that's kind of currently what I'm working on, is getting each motor synced up so that it gives me one straight line as opposed to these 2 angled ones. So I want to move on from the motors a little bit. I'm going to talk about the G code and getting that from Fusion 360, which is the CAD program I'm using. And I want to go into converting that and what needs to happen to the G code in order for me to use it in the machine. So I start in Fusion 360 and I draw this little triangle. The outer box is just like a reference that I set up, so I don't go outside of it and don't tell the machine to go outside like these coordinates. So it's just to help me draw the triangle in this case. And then I use the KM tools and the manufacturing tools built into Fusion 360, and I get some G code out that will draw that triangle. And this is what it outputs: a bunch of lines I don't need. So it's not like a super user-friendly. You get you just click output and it gives you G code. You can put it right into that. It's I have to massage it and kind of mold it and pull out just mainly the coordinates that it gives me, and maybe a few others. I can't do curved lines yet with that. I haven't added that functionality in. So I'm mainly focused on drawing straight lines and approximating those curves. And yeah, so my goal here is to kind of pull out the G01 straight line codes and put those coordinates in that. And how would I do that? I'm working on it right now. This is I've been working on a lot of other parts of this project, so I haven't been able to get to actually reading from a G-code text file. But I have some code that I wrote a while ago, just to kind of vaguely explain how I want to look at a text and read them as strings and compare them. This code, it reads that kind of top. It reads that top text, the G00, G01, G02. We're not using G02, but that was before I knew that. And then we're comparing them against this token that I set up down here. And basically the output that we get is how many kind of ASCII characters removed we are from that token. So in this case, I tell it to compare it against the G00, and then the output, it compares the G00 to G00. It's the same, so it's going to give me a 0. But if it's a G01, it's going to give me a 1, and I can manipulate, I can use that information to further the code and keep reading, but I'm not too far into this part of the project yet. Here are some CAD designs that I drew up. This is going to be real brief, but this is just kind of what I'm envisioning this final portion to look like. My frame with that paint module model I showed you earlier. It's really hard to make belts in SolidWorks and CAD software, so I didn't. But that's just some things I designed. I designed the feet, this little bracket in the corner, and a larger wheel, or larger tabbing gear, because the little ones I have on that currently aren't very, I want it to move faster, so I increased the diameter of the wheel for the tabbing gear. And then finally, for the user interface, I came up with this little design, just a little, one of our LCD screens, I think, that we have in lab. And I'm going to just use a keypad to kind of go through it and pick what I want. This isn't a great representation of what it would end up looking like, but I've kind of been iterating on it. So once we say, okay, I want to input a G-code file, we just, tab to that, or press whatever key that we want to go to input G-code. Then we pick the G-code file, and I would want to, then it brings it up, we put in whatever color that I've decided that the painter test G-code has to be on the paper, and we just click a start button, and it'll start executing that code. And then finally, I want to go over how I've been managing my project. There's a little bit at the beginning, I don't know if you can see, before this semester started, before I've been, last year, where I was looking into implementing USB. You can plug in a USB stick with G-code on it, and you could just go through the files like a computer, or a 3D printer, or anything kind of like that. That's way beyond my, way out of my league in terms of the skills that I have currently. So that's since been scrapped. And yeah, next I kind of that next block. It's just the designing of that paint module that I was going over before. The kind of the sections that I've been working on are kind of laid out like that in this presentation. But yeah, then I went through. I've been working on the motors a whole lot. Kind of the second half, and then the final kind of portion of the semester was supposed to be spent on the UI design, but I've been caught up getting the kind of coordinate systems to work. So that's not been happening. It's not going to happen yet, or hasn't happened yet. All right. I'd like to thank everyone for coming out here and listening to me ramble for the last 30 minutes. I think it was not fun for me. I hope it was more fun for you. And yeah, if you have any questions, I'd like to let you ask them now. And if you have any questions when I'm not around, my email is me. No questions? Are we taking it from the top? You better don't tell me we're taking it from the top right now.
It seemed like you were having fun here.
I'm having an amazing time. Yes. My timing here? I want it to move faster because that's a good point. I didn't mention this, but if I move too slow, kind of while I'm dragging the paint, it will cool and run like you kind of saw at like that in that beginning slide. I don't know if I can bring it out, whatever. But it's gonna run and it's not gonna produce like a line that I like. So I want cleaner lines. That's why I want to move faster. Yes. I think I was any questions. Yeah. That's going to be probably replaced with like a text file that I give it, and it's going to look kind of line by line. Like this is basically what it's going to see after I edit it a little bit, and it's going to see like just the G01s or whatever, and it's going to take the coordinates out of that and then give them to that machine, and then put it into all the math that I did, and make it go places and draw things and do cool stuff. Yes. Not now. I have to set a few things up, but I'm working towards doing the square that I showed it demoing earlier. And I have my laptop with me so I can input different commands and have it go to whatever coordinate you could possibly dream, whatever number you want. Yes, sir.
Anybody else have any questions for Peter?
Okay.
Can you check the can?
What?
Can you shake the can?
I have to be the one shaking the can. I haven't implemented that. I haven't made it so like it'll violently go up and down or try and get the can to shake on its own. No. Yes.
I think you may have mentioned this, I'm not sure if you said it this way, but your CAD front-end stuff,
Yes.
you have to draw the pieces in layers, right?
Not layered in the Z, like kind of layers in front of each other, but they have to be separate sketches.
But they'll overlap.
They will overlap, and I was going to add that, but it became.
So, get all the fancy effects, the blending and all that. It's really
It's a matter of me going in and drawing stuff in the kind of digital space. It's not supposed to generate art for me. I'm designing things, I'm putting them in, and it executes my vision.
This will make more sense when you have this mounted at its base and make it scale it.
Yeah. Yeah, the frame doesn't have to be there, but I need something to hold up those numbers right now.
Other questions? Thank you.
All right. Ask some questions, guys. I'm here. Have them.
Yeah, we've got a few more people coming in. That's great. We're going to move right into the next team presentation, or once they get set up here. You guys want to pull up your presentation? So just a This will be, there's a few points I want to make. I mentioned before, these are capstone projects, and one thing you did see in Peters is a great mixture of mechanical design, software design, and electrical design. So that's something we're looking for. These students can mix those technologies. We're going to see it here with this group as well. We have 2 electromechanical students and an electrical student here, and the electrical person has to do some software electrical design, where the electromechanicals are mixing 3 technologies. So look for that. That's a hallmark of all these projects. Are you guys ready? Okay, so they're going to introduce themselves and their project.
All right, so I'm Ryan.
I'm Daniel.
I'm Carlos. And we worked on a project to build an autonomous snow groomer that we've named the Groomba. So a little bit of background on why we made this project. So for those of you who don't know, there's a ski hill about a quarter mile away from here. And it's very rough in the winter, not groomed, so our task was to build a groomer initially, to groom the whole hill, and it got brought down to a subscale model of that, just so that it's attainable in the semester that we had.
So some of the constraints that we gave ourselves were we want to groom a 10-foot by 10-foot area autonomously. We want the plow to be able to fill and clear dips plus or minus 3 inches. We want it to be battery operated and be capable of being scaled up in the future. Right now, this project is only a scaled down version for proof of concept. So this is our,
This is our system diagram, the physical system. So in the middle there, feature on a hill is the actual Roomba itself. And then we have 3 beacons around here that are transmitting to this receiver. That's how the navigation system is knowing where the groomer is and what direction it's facing and all that good stuff, so our navigation system can do what it needs to do. Then on the front there's a plow, on the back there's a tiller and a rake, and then these little screws here are how it drives. There's one on the other side. It's a little bit blocked right now. Basically the plow will smooth out any big divots plus or minus 3 inches. And then it'll drive over them, and then the tiller will till the snow, make it nice and soft so that the rake can pack it down and give it that signature corduroy look that you're used to seeing on a ski hill.
So here's our software system diagram. As you can see on the left side, the beacons in yellow, beacon 1, 2, and 3 are the beacons that you saw in the corners of the hill. They are not on the groomer. Everything else is on the groomer. And in gray is our main system. So we have the Bluetooth receiver that's receiving the data from the beacons and figuring out where we are on the hill. The magnetometer is figuring out where we are faced, if we're tilted left or right. And then from there, the main system is giving our obstacle avoidance, our target velocities for our screws, so we know we can set where we're going and how fast we're going. And then we are giving some data back to our tiller control system that is reading forces from the load cell and keeping a constant force on the ground. And our plow control system is being told what state it's in.
All right. So if you take a look at this image right here, I know there's a lot to look at here, but this is a image that demonstrates sort of a eagle's eye view of what the system would look like for the navigational system. So these are the beacons, 1, 2, and 3. This would be the Groomba right here, and it will start here and here, and then we'll have a map. It's positions, points where it should go to in sequence. And then it also has, apart from the position, it also has an angle reference of where some angles that should be matching. And that is part of the mapping that we'll get more into later. And then this is the 10-foot by 10-foot area. If you look towards the right, you will see a system diagram for the navigational system. These are the beacons that are transmitting data. You have the scanner that's receiving the data. And then after we get the data from the scanner into our microcontroller, just a separate communication. Then the microcontroller can make a decision, check which beacon it's talking to, and then from there it gets the distance and the angle based on some characteristics from the Bluetooth signal that we'll get more into later. So again, this is sort of an overview of my system. These are my three subsystems that make part of the navigational system. It's the positional system, which is generating the XY coordinates, whereas the Roomba inside of the 10-foot by 10-foot area at all times. And then for this, I use Bluetooth, and I use the beacons and the scanner receiver inside the Roomba. Then for the orientation subsystem, I use primarily the main angle source would be the Bluetooth with the beacons and the scanner and receiver. But then I have a backup plan, which is a magnetometer, which is a magnetic field strength sensor. And then I will be using this in the event that this is not a viable solution. And then I will get more into that later. So briefly, this is for the RSSI, which is radio signal strength indicator, which is a number that roughly tells you how strong the signal received and the Bluetooth signal that you're receiving is. And this number right here, this is how I receive it. This is a waveform with all the data that I need from the beacon inside of this is being received by the receiver. So these two numbers over here are the RSSI, and then these numbers over here are the address that I can use to identify which beacon I'm talking to. And then right, so I'm communicating with the receiver that gets this data into our microcontroller, the 25C, so I can actually process that data further. So the RSSI in and of itself doesn't really give you distance. You have to do some more work to get the distance out of that. And then I had to do some testing to figure out an equation that would give me accurate precision based on the RSSI that I was measuring. And so I did some experiment and I got this equation from Randolph. This is the plot for it. And I tried some other methods and then I figured out which one had the smallest error, and then I used that one. Now to the real positional calculations and how this really works. The idea behind it is geometry and Euler's formula right here. This formula lets you calculate the area of the triangle with 3 different sides. And the reason why this is important is because if the Roomba is over here and our beacons are positioned in the corners of the 10-foot by 10-foot area, then we can use this triangles form by the distance between the Roomba and the beacon to form these triangles, which then we can find the area, like I said, with the Euler's formula, and then use the fact that the area of a triangle is 1/2 base times height, you can see over here, to flip that equation, find the height. And that height would be a diagonal, parallel line, from where the Roomba is to this line created by the beacons. And then that basically is the distance between the Roomba and this one right here. And then, as you can see, that is the distance in the x axis, and then this is the distance in the y axis. So over here I have an example with this exact point and this exact length. And then it gives you a point of roughly 6 and 7.5 feet. that will be the coordinate of the Roomba at that point. Now for the orientation and the angle, I have two cases that I'm going to go through. So in the first one, the Roomba is looking forward, so it's facing towards that arrow right here. And the idea of the problem that I was having is that the fact that the angle that you measure is dependent on, first of all, your position, but also the orientation of the Roomba itself. So it's not dependent on one single thing, it's dependent on two parameters that are always changing. So I have to figure out some reference to help me be able to determine which is the proper angle that it's actually facing. So over here you will see if the Roomba is facing forward like this, then this angle from this beacon would be in this first quadrant, or otherwise, in other words, it would be below 90 degrees, which means that I can just take whatever the angle is, and it will be accurate, right? It will be this angle right here. This will be the angle from the beacon, and then from the second beacon over here. But if the Roomba is facing the other way, opposite way, then now that angle is different, because now if you want to see what the angle is, you have to turn all this way around and get a bigger angle. So that's why the difference to the angle, even though the beacons are in the same spot and the Roomba is in the same spot, it's rotated differently. And now for my backup angle measurement, it's the magnetometer. It basically just measures the strength of the magnetic field, Earth's magnetic field, and it can be used to generate a digital compass, which will tell you 0 to 360 degrees. So you can rotate it and tell you what angle you're measuring, or what angle you're facing in reference to the Earth's north magnetic north pole. And now, again, back to the mapping subsystem. So this subsystem would have X, Y targets, or points that the Roomba should reach certain points in the path that I create for it, which is the zigzag path. And then it will have some angle that the Roomba should also face. So the idea is that we compare the actual position and actual angle of the Roomba to the targets, and determine how far it is from that target. And that information would go to the dance system, or the driving system, to determine how fast the motors have to spin, or which direction has to spin, how much, so that we can reach that target. Now, other issue that I faced with the Bluetooth technology is the fact that it wasn't accurate enough, and it was very inconsistent. I wouldn't be getting a precise constant distance estimation from the beacons. So I had to switch to a ultra-wideband technology. Similar, it's a transmitter receiver. Much of the math is the same. The takeaway is the fact that it's more accurate, and it gives me consistent measurements of the distance, so that I can actually reliably tell what this Roomba is at all times. Then another thing is the fact that if I switch from Bluetooth, I miss the angle measurement from the Bluetooth signal. So now the magnetometer is my primary angle measurement. So again, this is highlighting the fact that I switched from the angle of arrival, which is the measurement of the angle of the Bluetooth signal, which is done with two antennas. You have to measure the phase between them, which means it's measuring the difference at the angle that you're receiving the signal from. And then this is the magnetometer that I explained before. And over here you can see the difference in my system diagram when I include the magnetometer. And now for the time of flight versus RSI. this is what time of flight calculation looks like. So over here will be beacon 1, and then beacon 2 will be over here. And then again, beacon 2 will be over here. And then the idea is that the one beacon sends a signal, and then it will wait for a reply, and then it will keep track of the time that it sent the message, the time that it received it, and the delay between them. And then we'll use those values to calculate what is known as a time of flight. And then this time of flight can be multiplied with the speed of light to get the distance. So now this is the math that goes into the new beacons and scanners to estimate the distance, and it's much more accurate and more reliable.
So one of the first tests that we did to figure out some of the numbers that we needed was filled up a box that was approximately the size of the plow that we wanted to make. We filled it full of snow, and then we had a little fish scale on it, and we pulled that to see how much force we would need at the tanks and the plow, and it came out to about 25 pounds of force, and that was one of the goals that we set at the start. The threaded tanks that we are using for the travel of this is one of the main subsystems. What you can see on the left with the encoder, motor, and pulley is only half of it, and this would be at the front of the tank here, and it would be mounted with a pulley here from this pulley with a belt right onto the tank. The gear ratio is a 1-to-1 because we wanted to keep the torque very high at the tanks. And the speed that we're controlling these motors from can be controlled individually with our left velocity and our right velocity that we set in code. Here's what the control system looks like. So we have the obstacle avoidance system from the very start that's feeding our controller the target velocities that we want. And if we were to say we wanted to turn the Roomba to the left or right, we would vary those target velocities, and the controller would try and change the speed of the motor to get to that speed that we have in code. And this is what it would look like if we were going straight. You can see in the middle, we would have both of the motors going at the same speed. And if we were going to the right, we would lower the right target velocity and keep the left target velocity the same. And that would move our whole system left or right. When we got everything together, we needed to figure out the actual size of the motors. So we scaled these for worst case scenario. We put this whole system on the ground and measured the torque we needed to actually spin the motors on carpet and snow. And in carpet, it was a lot more, about 6 Newton meters. And then when we were looking for motors that were in our price range and the specs that we needed, we just went with 8 Newton meters because that was a safely over our required size. And then here's a little demo of it. The video that it should show is the one on the right, and you'll see it going straight at the start, and then I will change the target velocity so it starts turning to the left. So it went straight for a little bit, and then I cranked the target velocity so it turned all the way to the left. And this other video is just the target velocity staying the same in the snow.
And then this is the tiller subsystem. So this is what will be on the back of the groomer that's making that final corduroy pattern, making that snow nice and smooth. And so the system uses a DC motor with a belt to spin a tiller. It's basically making the snow soft, like you would imagine like a rototiller does for a garden. And then after it goes through that, the comb's smoothing it all out. And the whole system relies on a load cell mounted to where an actuator is mounted on the frame right here. And depending on how much force is being applied to that load cell, it'll raise or lower the whole assembly to keep a constant force to make the terrain nice and smooth. And then so a little background on linear actuators. We actually use one for the tiller, as I just said, and there's one on the plow as well. We'll go into that system a little later. But just for pricing, we picked these linear actuators. They're very simple. They're functionally the same as like a hydraulic ram would be. And these ones particularly run on 12 volts and they can push up to 300 newtons, so they're more than strong enough. And then so the prototyping, there's a few SolidWorks models here. So this is what we have. It goes on the back of the whole assembly. And like I said before, it's belt driven from, there's a motor right here, goes around the tiller inside. This is what's inside here. And everything is meant to be easily replaceable if something does break and be strong enough to not break. And the electrical diagram is pretty simple. I have my KL25Z, same computer that Peter's using, and then it goes into a motor driver, and there's a control system I'll go into in the next slide, but is sending a different pulse width to the motor driver to change how fast this, or to change where the linear actuator is traveling, change which direction it's going, to keep the tiller on the right pressure. So we have a desired force here in the control system, which is where we want, like how much we want to be pushing down the snow, and it compares that at the end to how much force we're actually getting, does the comparison, and then the controller tells the actuator to either move up or down. The actuator does it, and the end result is the tiller should be maintaining its constant force on the ground. This is just a quick little demo of it, so I'm going to push there's a red button you'll see in a second. It's not in the still shot, but it's there, and the tiller inside will spin for a few seconds, and then I'm going to push up on the actual comb, and it'll lift or lower the tiller depending on how hard I'm pushing. It's really hard to see it going, but you can see it kind of in there. As I push really hard, it moves up. If I let off, it goes back down. So.
And then now we have our plow subsystem. So in this subsystem, the two main points that I'm focusing on are the ultrasonic sensor that's actually seeing the top of the snow in front of the plow, and a potentiometer on the base of the plow that is reading the position of where it is raised or lowered. So these ultrasonic sensors we're going to be using a couple times, so a quick explanation of them. We have them powered up, and then we're sending a quick little signal to the trigger pin, and then we are waiting for the echo signal to come back. And with those two timestamps, we can figure out how far away an object is from the sensor, and we can get that in a measurement distance. So here's the plow design. You can see up on the top left is the echo sensor, and this is seen to the top of the snow and coming back up, and that's how we figure out where we are. And then this plow is getting raised and lowered by this linear actuator to try and keep about that same distance, and it's seeing where it is with this little potentiometer connected to the arm that is lifting and lowering with it. So here's the control system. We have the desired distance, which would be the distance we're seeing from the echo sensor, and then it's getting checked. Sorry. We have the desired distance that we're seeing from the echo sensor, and if that is too high or too low than the measure it was just seen, it's adjusting the controller, so it's raising or lowering the linear actuator, and the feedback is that potentiometer on the base of the plow. So if the echo sensor is seeing that the snow is really close, it's going to raise the plow up until it sees that on the potentiometer that it is in a raised position, and then it will be happy and keep going. And so here's a quick little demo of the plow moving. So at the start, you're going to see me raise it all the way to the top, and then all the way to the bottom, and then I'm going to hover it at a few different places, and you'll see the plow follow the box that I have. It's a little funky at the end there, but it was working, I swear.
And so this is the obstacle avoidance system, and it really acts as kind of a filter after the navigation system gives us our targeted velocities for the left and right controllers. They go into the obstacle avoidance system, and all it's doing is scanning to make sure there's an obstacle like this tree here. If there is an obstacle, it kind of takes over and sends different target velocities to the motors to avoid the obstacle. So the parameters are there needs to be able to see objects greater than about 1 inch wide, 3 inches tall, because if it's smaller than that, it's like a bit of grass or something that it can just run over, it's not a big deal. And then after there's no obstacle, the flag is all clear, and the navigation system can take back over and get the group back on path. This is the electrical diagram. It's really just 5 ultrasonic sensors that Dan just explained how they work, mounted at different locations, pointing in different directions, and it's just inputting, it's taking all of the data from those, and comparing them, and figuring out what the best path is. And so this is that software diagram. I have ultrasonic sensors, there's 5 of those, like I just said. They go into the main controller, and then there's a bunch of kind of scenarios laid out for it to give desired right and left motor targets. And then so the goals for this system are to be able to go around a bigger obstacle such as a tree, and then like I said, if it's a blade of grass, you can just run right over it, which I think it does a pretty good job of. We'll see on the next slide. So this is the demo that I have, and it's programmed right now as if the navigation is telling it to go straight all the time. So unless there's an obstacle, it'll just drive in a straight line. So it sees that there's a table leg there, it'll start to turn. If stuff gets too close, as you can see, it backs up and really turns to make sure it avoids it.
So one of the big problems that we had to figure out was our runtime and battery sizing, because we want this thing to be battery operated and not have a extension cord running out to it. So we had to figure out some of the bigger power drains that are going to be the tank motors that are spinning the 2 threaded tanks, the linear actuators that we're running, and our KL25Z, which in total gives us about 16 amps total if we were running everything full power all the time. And so with a 50 amp hour battery, that gives us about 3 hours, which would be more than enough time to demo the whole thing running at the same time.
Alright, so over here we can see our UI. This will be in the snugger. Then we'll have a LCD screen, start button, emergency start button, and a turn on button for the unit. And then this display will be used to display basic information about what the system is doing. And then again, the key part of it is the emergency start button. If anything's going wrong, just press that button, it will start the video.
And so our budget for this project, our goal is to stay about around $1,000 or under, which, as you can see, we ended up buying a lot of stuff. Some of the stuff we didn't end up needing, but it was for testing. We ended up spending around $930, which is under budget, so that's good. And then, so this is our timeline. So as we can see on the top, I'm in the red, Dan's in the green, Carlos is blue. So we all started with our first subsystems that were last semester before we made the schedule. So they're not super detailed. And then at the beginning of this semester, we all started working on our second subsystem. So I started working on the obstacle detection system, obstacle avoidance. And as you can see, there's some milestones there, such as building the frame to demo it on, because that's something I needed to do. And then go to the end.
So I started working on the angle with the Bluetooth. That was the first thing I was doing, and then I transitioned into doing some of the beacon PCB design, because I wanted to have the beacons in their own enclosures that was separate from the rest of the system, and that they could be battery operated. And then my final task was to do some testing and troubleshooting. And then, of course, it's not in here because it just happened recently. But over here, you can see the change I did of the Bluetooth to ultra-wideband technologies.
So my first subsystem was the frame and driving. That took up a lot of the first part, and then when we split off, I'm in green, and you can see I started working on the plow. So my first big milestone was get the whole thing designed and start printing it. And then my second big milestone was getting the finished subframe designed and the code finished. And then in the bottom in black, you can see as a group, our goal is to have this all together and fully functional next week, which we're going for still, but yeah. And thank you for hanging out, thank you for watching. We can answer questions, and we also have some stuff over here that you can look at while the other group is setting up.
I do it constantly. Yes. Yeah, this is just for the position. Takes a couple, well, with the Bluetooth it takes like 3 seconds. With the ultra wideband it takes like 6 or 7 seconds.
So you're creating information in your system, updating in every concept.
Yeah,
That's going to their system.
correct.
Line or Dan, you need to wonder before you. You didn't actually show up after. What is this really? Is this a one-time calculation?
No, we would be getting the numbers fed. These target velocities would be getting constantly told to us from the obstacle avoidance that is getting values from Carlos's system. These would always be changing, but wouldn't be drastic changes in between two measurements. Milliseconds. I'm basing my target velocity off of the last number that I was told.
So the system you just heard about is 3 computers all working together, different time scales. Carlos's can't get updates faster than every 5 seconds, but Dan's and Brian's needs to operate at a much faster time scale, and their stuff is all happening really quickly until either an obstacle is ejected or Carlos gets in the new location. It's hard to show that in PowerPoint. That's why you have to see it work. But hopefully you appreciate the fact that a ton of effort went into thinking through this multidisciplinary, multi-part project. And I'm going to stop talking. If you have any questions you can ask, why don't you show us what you did?
So you're telling me that nobody rooms this little ski hill here for the students to use?
No, it gets pretty rutted out and chunky.
So if you guys can get this thing going, has the school talked to you about implementing the Roomba? And if so, do you think more students would recreate on said hill?
I mean, everybody who is a student and has skis is welcome to go. It is not maintained, so this would definitely make it a lot better than going to a ski mountain.
And is it free to use if you're a student here?
Yes.
Wow. Great idea.
I have a quick question. So
So our first idea was we wanted to do tank tracks, but I wanted it to be more of a piece that you could look at and be interested in running instead of tank tracks. So that was the main motivator to doing that instead of tank tracks. The time put in, the 3D model of it took a while. That was easily multiple days of multiple people and Kevin helping us with it. But once we got it printed, it was a lot easier to work with than tank tracks, I think, because that is a motor, a gear, and the torque that it produces is a lot more than we need.
Well, it also seems like you would get a much better grip. I mean, that's a fact. It's going to grab more of the tires or the tracks. But it wasn't hard to control. You got to steer it.
No, you can see it over there. We called it the gamer knobs. It's just two little potentiometers that we can adjust the target velocities in code, and that's how we were controlling them in the videos that you saw. Yeah, the first time we demoed it was right after that massive snowstorm where everybody was losing power, and we set it up on the side of the walkway, and it started running right into the snowbank, and then it just kept going and was pushing like a foot of packed down snow in front of it.
The slide where you had the path layout, was that predetermined or is that kind of set on the scale of the
The path is predetermined. I just put some target points in there. There's no math that goes into the path itself.
And if the obstacle detects something and it deviates from the path, how does it get back on its original path?
So I have a piece of code that determines what the closest point to the path is, in case you get it out of the path and it tries to find the closest point, and then it tells you the distance and the angle that you have to update to get back into the path, and then from there get back into the predetermined point that has to go to.
I have another question. The beacons. On a real trail, do the beacons, like, are they permanent? Do you have to put them in?
Yes, they are in stakes,
Okay.
and then you can just put the stake down and wherever the location has to be. They have to be in certain distance apart from each other. The same for all of them. I will be demoing that over here. But yes, they can be put in place and after the taken off. GPS, as far as my research, when I did the research last semester, it told me that the accuracy was like 1 to 3 meters. So, right. Exactly. Because our area is so small, we can't be doing that much of it.
Walk over here, we can stretch our legs, and
So this is the tiller setup here. We have this button here, and you push this, it runs for about 3 seconds, turns off, and that's an independent system then raising and lowering. So if I pull on it, it'll try to fight me. I'm fighting really hard. Yeah, this was working better. I tested it more of a lap.
I believe
Over here.
you have video that works.
I don't know that. Okay. Oh, I know that. Nope, that's not it. Not it. I know that. Yeah. This was working before. I had no idea what happened. It was working fine before. Okay, there we go. I was pushing a little too hard. So it tries to maintain a constant force on my hand. So it's fighting, I push up harder, it'll raise. If I let down, it'll come down. It's a little jittery, but. anybody wants to push on it and see how hard it pushes back, you can. Or one of the next ones.
Somebody go up there and push on it. Great volunteer.
All right, then.
It's quite hard.
Yeah.
It literally, okay, yeah. No, it's
So the
not
control
happening.
system and the reactor are maintaining a constant pressure.
It gets upset sometimes.
So that way it can sort of follow the contours of the ski hill.
And then that force that it's pushing back is user set, so it's probably set a little higher than it should be right now, but I can change that eventually.
And then here's the plow. So this is reading a distance from this sensor and we're trying to keep the plow following that distance. So you can mess with it all you want, but it'll keep following the distance you set. It's a little jittery when it gets to a resting position, but if anyone wants to. It's a lot. Keeps going. We get it.
So this was the little demo car that I had set up to kind of demonstrate the obstacle avoidance. So it'll just kind of drive straight unless like
Explain why you have the
obstacle
car.
comes in front of it. Well,
Why did you use the car instead of just putting it on the
So-
main system?
the frame, the driving wasn't completed when I had to start working on it, so it'll kind of just see stuff. I needed a way to demonstrate that the system worked. So
But it's actually using Dan's software for the velocity
Yes,
control, right?
yes.
So it would, the actual Roomba would be going like this speed.
Yep.
And instead of wheels, it would be those screws.
Yep.
Yeah, they just needed something convenient they could drive around the lab and test out the obstacle avoidance.
We can't demo that. Carlos, are you ready for your demo?
Okay, that was a demo.
I have Yeah, speak up, Carlos.
I can show you the positioning and the angle orientation demo. So it would be hard to say because it's always when you come into the screen. So I can show you the positioning and the orientation demo. So it would be hard to see because this is down in the screen. But these are the beacons. This is the scanner receiver, and then this was the inside of Ruba. And if I move it over here, which is technically the zero position where the shoes are, it takes a couple seconds to update it. Right now, I'm saying that zero in the X direction, which is this direction, because it's at the starting point, and then it's saying that it's 10 in the Y direction. I guess I put the beacons on
So the beacons are in the wrong place?
Yeah, I should be measured from here. This is actually the 0 position. But if maybe Dan or someone wants to verify that it actually says 0, and I'm not lying,
Do what?
you just read that.
Oh, pick that up.
Don't pick it up, just read it there.
Oh.
You just read what it says so that people actually believe me.
It's reading 9.6 and 0.3. So it's almost 10 feet this way and 0 in the y direction.
Yeah.
Put it in the middle.
And then if you put it somewhat in the middle, it's saying it's 6.7 and 5 feet. So anyway, that's the amount of screen.
So we're dealing with distances that are very small compared to the speed of light. Why is it taking 6 seconds to figure out its position?
I don't have the answer to that. I think it's something in the code. I think it might be multiple sensors for the reason. I'm not sure. I don't have to for this specific. You guys have some libraries for the position and stuff. So I'm not very sure if it's a long
What is the other one that was
So this one over here is demonstrating the angle measurement. Over here I have the magnetometer and the microphone frequency. And then as I turn this device right here is the micrometer. So as I turn it around, the angle changes. And it's basically a digital contact. Both of the reason why I can show the mapping subsystem diagram is because I need to integrate the position and the angle together. So I'm having issues with the communication with that device, the microcontrollers. And then I'll be working on that this week, and then by the end of this week, we should have hopefully navigation on this page and I can demonstrate it.
Any other question? All right, thank you. Normally we would have refreshments. I'm hoping they'll bring them, but absent the refreshments, we're gonna allow the next team to start. And but at any, if you want to take a few minutes and just talk to these teams at the end, that would be good. You can get a closer view of the projects. Again, this is a larger group, 3 students that each have a lot to do. And in addition to doing mechanical, electrical, and software design on their own parts of the project, they have to interface with their teammates. So that's another layer of design that it's hard to see until you think about it and see it laid out that way.
And they have to talk to each other.
They have to talk to each other. Occasionally talk to me. Yeah. I think I'll just let the other team introduce themselves. So give us a few minutes to get everybody back in their seats, and then we'll move right into the air hockey robot.
Hello, everyone. We made the Puck Paladin, which is our air hockey robot. And I'm Josh, and this is Tristan.
So, as you may know, air hockey is a 2-person game, and we don't like that. We like 1-person games. We designed a robot to replace a player. Theoretically, it's gonna play an intelligent game of air hockey.
So here we have our system diagram. This is our system diagram. So here we have, this is the human player, and it all starts with the detection of the puck, which we use the Pixie 2 camera. That takes that information, brings it over to a microcontroller that does all the math. Then I communicate with Tristan's microcontroller for the robot arm, and that controls these 2 motors here, which move our 2 links, which has a hammer or a paddle, whatever you want to call it, at the end, and that will allow us to interact and play a game of air hockey.
So this is our block diagram. It's got, basically we have 2 power supplies, the 5-volt for the 2 KL25Z microcontrollers, and a 24-volt power supply for the motors. Our Josh's side is over here. He has his KL25Z microcontroller controlling the Pixie 2. My side's over here. I'm doing all the motor stuff, and yeah.
The first thing we're going to go over is object tracking, because it's the biggest step, the first step that you really need to take when playing any sort of game. And so object tracking is basically a camera that takes pictures and it processes those pictures looking for certain colors of pixels, and seeing groups of pixels will allow it to identify different things. Like here is an example of it identifying two separate things. And this is how our puck looks on our screen. See, it doesn't have the highest resolution, but it has a very high refresh rate, which allows us to constantly be seeing the puck. And this is the Pixie 2. And it's what we're using to track objects. It has a lot of the systems that look at doing pixel comparison for color built into it already, which allows for a lot less processing time on our end. And it's already optimized to do basically everything we need. You can just train it to any color you want, and then we get data out of it. So we went with UR communications, which is universal asynchronous receiver transmitter. So the easiest way to describe it is it takes a wave and it goes up or down a set amount of times, and each represents a 1 or a 0. And then from binary, it can be converted into a usable number. And of all of this data coming in, only a small part of it is necessary for what we're doing. They give information on the size of the object, which object it is in frame, but we only care about the X and Y coordinates of one object, which is the puck. So we can refresh that ridiculously fast. We get the data. It takes less than 2 milliseconds for all of the data to be transferred over. It takes a little longer for the Pixie to send the data. So this is a small packet of data that comes about every 40 milliseconds, and it only takes 2 milliseconds for the actual data to be passed through. So when I get this data, I put it into a nice array over here, that's all of the different parts coming in. And with all those parts coming in, the two parts I need is this 10, 11, and 12, which here on this example board, you can see this is the X and Y coordinate of the puck currently, and I'm getting the X and Y coordinate here. The reason that 11 is underlined is because it's 8 bits of information being passed through with each number. The maximum number it can go up to is 256. No, 255, because they count 0. And if it goes above that, this number will go back to 0, but the next one will become a 1. So I have to account for that and look at it and say, oh, this is a 1, add the rest here. So that's the start of the code. That's how we get our information. And then what do we do with it? So here we're doing a lot of just finding the slope of the puck, finding where is it going, where is it going to hit the goal line? Because at the end of the day, we only really care about blocking a shot if it's going to go in the goal. Because when time is of the essence, moving to block a shot that isn't going to go in anyways gives potential for that bounce back if you don't get there fast enough to be you now out of position when trying to block. So if the puck isn't going to go into the goal, we don't react to it because we don't want to be out of position for the next shot that may be potentially going to the goal. So here is this basically saying, hey, is it going in the goal? And if it is going in the goal, it takes the slope that we find in the very beginning, puts it to a set X value, which will tell you how far away from the goal you want to block it. Then you just calculate for a Y, it gives us a point, and that's where we tell our robot to go. And a straight shot's pretty straightforward, but bounce shots are a little more tricky. So here we have the general idea of how you calculate a bounce shot. And in the bottom we have an example that I did for my first subsystem demo, which these are the previous positions, current positions, and then projected where it will go, and that open end would be the potential goal. The reason you'll see some values are negative here is the the Piximon software actually flips your Y coordinates in a way that makes it unintuitive to work with. But this is what, with this shot here, with the first one being around there, second one being around there, it will project where it will end, and it does so fairly well, and enough that we can tell where it's going to go and how to defend it. But just getting in the way is fairly easy to do. So this is the looking at, it's going to go into a wall. This recalculates the angle. Now we know where it's going. The code all sees it, sees whether it's going to hit the bottom or the top, changes the formulas you need depending on which wall it hits. And then just getting in the way is fairly easy, so we want to be able to control where the puck will go after we block it. So this little diagram I made here is a little simpler than the whole math done out. So angle in is this green puck is coming in at this angle, and we want to block it so it goes straight to the wall. So then we can slow the puck down and then play offense on it. So to do that, we take this incoming angle, we take the angle we want out, we bisect it. For those who don't know, that's go right in the middle. And we follow that down, and we want to be the radius of this circle and the radius of that circle away down that line. Throw some tangent at it, do some more math, like this down here, all this, and then it will give us a spot where we can go that will allow us to properly block so it goes straight towards the wall. And then now that we have all of these different ways of knowing where to go, how do we get this to the robot? So if here robot set is basically saying, is there going to be a goal? Do we have somewhere we have to be? And if there is, we're going to one of those, whether it's a straight shot or a bank shot, it's going to that set location, and it is sending it in this list of characters. And it sends it in the UART style with the ups and downs. And the middle two numbers are the two we care about here. These numbers around it are just used to verify that the person who's receiving the data is getting good data. If you see that you're getting two numbers before and after, you know that the two in the middle are most likely perfectly fine. And then if I don't see any goals blocked, we go to our home position, which is fairly close to the goal in a centralized location, which allows us the least movement for the most possible angles that can be hit, which all of that is controlled. All of this is in a sys-tick loop, which for those who aren't too familiar with electronics, sys-tick is an interrupt timer, which always counts at the same, it'll keep counting no matter what else is happening. So I'm receiving data every approximately 40 milliseconds. I want my loop to be as close to 40 milliseconds as possible, so I'm always picking up that next packet of data before I read the previous one. And to do that, I have this certain timer and this one up here, so all the data is gotten in the same amount of time, sent at the same timestamp, so there's no confusion between multiple signals.
So, I was in charge of building the robot arm. It's called SCARA, that stands for Selective Compliance Articulated Robot Arm. Selective compliance doesn't need to matter to you guys. Articulated basically means that it's got two joints and acts in a similar way to most robot arms that you see are considered articulated robot arms. In this case, we have our motor shafts in line. Each of these gray things here and here are one of our motors, and one of them is directly powering this first link of the arm here. The other one has a pulley here that connects to this pulley at the end via a belt that's also not pictured. And that top motor will control the second link of the arm. So for our motor requirements, we have a few simple things. We need a required torque of 11.24 Newton meters and a max speed of 120 revolutions per minute, and it needs to get to full speed in an eighth of a second. This is all because anyhow puck moves really block it. The required torque gets you up to speed in the correct amount of time. Yeah. So we have the SCARA mounted on two vertical pieces of 80/20 aluminum extrusion. That's basically just a square piece of aluminum with some slots in it that you can fasten things to really easily. The belt I mentioned is a steel fiber timing belt with an 80-tooth pulley. The links are each going to be 12-inch. They're not going to be, they are 12 inches of carbon fiber tubing. Most of the parts are 3D printed out of PLA. That includes the joint, which is shown here in red and blue. The motor mounts shown here in yellow, the brackets in green, and the end effector, which is not pictured in this. So 3D printing our mounts and braces. This is, like I said, the motor mount. This is where I place my encoder. An encoder is a simple sensor that tells you how far you have gone from an original position. This brace here holds either, it holds the first link, and there are two of these braces. One of them holds the first link, the other one holds the belt pulley. So we also have a bunch of 3D printed link fasteners. This right here couples the first link of carbon fiber tubing to the motor shaft. The motor shaft is a key tool shaft, so you can see there's a little tiny notch in it. You've got a small piece of square steel that fits into that notch, into a notch in the shaft, and directly causes that to revolve. The end effector holder holds the end effector. The end effector is what we call the tool or whatever you're using at the end of the link. In this case, it's the air hockey mallet. This is the fork joint and the knife joint. The hole in the knife joint and the hole in the fork joint align, and similarly to the shaft coupler, the knife joint has a key so that it can easily be manipulated. Last but not least, the end effector stopper holds the pin. There's a small pin that holds the top, not the top of the mallet, to the end effector. This holds the pin in place. So, this right here is a bunch of math. This is how we figure out the angles that I need to send each link of the robot arm to based on the end effector coordinates. So Josh is giving me a pair of XY coordinates. In this case, it's in pixels. I have to convert them into inches. And I use these formulas here to this is the derivation for the formulas. The next slide is the actual formulas. So right here are the two formulas that whole page was deriving. We have two congruent lengths, which is just makes everything easier mathematically, and also can ensure that the goal can be protected while base centered. And x1, x2 is, or x2, y2 is the end effector position, and to determine the angles, theta 1 and theta 2, the formulas are applied. This is the code that does that. So this is the first formula right here, and that is the second formula right there. Next, this converts the formulas from radians into degrees, and right here, this is to verify that we're going to the right places. So, I have to control two motors. Similar to everyone else, motor control is kind of a pain. going to be a bunch of math dedicated to how I analyzed my motors. To start out with, we have a very typical motor transfer function. This relates the angular velocity, or how fast it's spinning, to the input voltage, and does that in terms of two parameters called K and T. The T is the time constant for the motor, and K is the motor gain, which is calculated by taking the motor's speed and dividing it by its voltage. The time constant is actually measured right here. Right about here it is 2 milliseconds, and that's where it gets to its steady state. It doesn't look like steady state because this is moving fairly ridiculously fast, and I didn't actually have enough time to get in. The program ran too fast for me to effectively get more data points than are shown here. So I decided I wanted a gain crossover frequency of 100 radians per second. That's fairly slow, which means that the motor will respond fairly slowly. If I'd chosen a higher gain crossover frequency, such as 200 or higher than that, the motor would come up to speed faster but might overshoot. Now at 100 radians per second, we can see right here that we have a magnitude of 6.35 decibels and a phase of 101 degrees. Those are important, so I wrote them down. They're used in these two formulas, which are used to calculate parameters called TI, the integral time, TD, the derivative time, and KP, the proportional gain. Now, these parameters are stuck in this function, which actually theoretically controls the motor. But we have to convert it into a different domain first. So, before we do that, the formula that we had was what's known as a PIPT controller formula, and I wanted it to be a little simpler to implement, so I wanted to convert it to what's known as a PI controller. Now, the PI and PD and PID stand for proportional, integral, and derivative, respectively. To convert the PIPD to a PID controller, we followed this math shown here, and essentially took our integral time, derivative time, and proportional gain, and converted them into a proportional, the proportional gain for a PID is the same as it is for the PIPD. You have to convert the integral time to an integral gain and the derivative time to a derivative gain. Now, once you're done with that, you have to take it from what's known as from the analog domain, so to speak, to the digital domain, which says that in the analog domain, you don't have any discrete time frames. In the digital domain, you have to iteratively do this math pretty much every time you loop. In my case, you're looping every 200 microseconds, so it'll do this math 5,000 times per second. Now, this is the code to do all that. Really, it's much less complicated to code this than it is to do the math. Once you've got these two formulas right here, you're pretty much good to go. But the main point is that you have to calculate these parameters K1, K2, and K3, which are based on Kp, Ki, and Kt, and fit into this formula to... I was putting up the wrong formulas. These are the formulas I want. They include K1, K2, and K3, the three gains in question. This is my motor control diagram. This right here is a step function, which means it's going to a specific point. In this case, you're considering it to be a specific angle. Your target is, this is a summer. What that does is subtracts what's over here at the very end from what's here. And what that gets us is what's known as an error, which tells us how far away from our target we are. Now, then we give that error to the PID controller that I was talking about. It figures out how fast you want your motor to go at that particular instant in order to effectively get to the position you want. And it'll recalculate that every 200 microseconds, like I said. It can sometimes output a number bigger than you want. So what you need to do then is use a saturation block to limit the numbers you can receive, in my case, to under 250. A bunch of people have talked about pulse width modulation. What that means is I have, there's an on and an off time with a square wave. The on time is an amount of ticks out of the 250 that I mentioned, which will, and that is proportional to the voltage that you are theoretically sending to the motor. This is that conversion that I was mentioning between the voltage and the pulse width modulation. This is actually the motor transfer function that I was talking about. Now, right here, all of this stuff only gives you an angular velocity, but I need to go to a specific place. So this is an integrator. That turns your angular velocity into a position. Now, that's in terms of revolutions, which is unideal. So here I convert it to degrees. And I need it to be in terms of my sensor, the encoder that I mentioned earlier. So this converts the degrees into how many encoder counts, which is finally fed back into the controller. So this is a little video of the PID controller working for the first time. It goes to specific positions and returns where it wants to go.
So I worked on mounting the SCARA robot. So what I decided to do is, for the robot, I wanted to go underneath the table because we do not own the table and we need to do minimum damage as possible for mounting purposes. And I have this nice square bracket underneath, which is completely customizable, so we can move the robot along this however we want. We can also move it further out or further in on these sliders here. And this is the robot on the stand. All stood up right there. And then, mounting the Pixie 2, we have some 3/4 inch conduit that we use as a frame, which is held together by some 3D printed brackets and is mounted on the side of the table. And the Pixie is in a little case like this, way up at the top there, so it's looking down with a bird's eye view on the table. And then we have wires that go from the Pixie 2 down here, down to our microcontroller. So this is the general split up of responsibilities for this project. Was the camera tracking, mounting the SCARA robot, and then I did a lot of the basic gameplay and understanding how giving X and Y coordinates for the robot.
Meanwhile, I made the robot and made it go to the XY coordinates he gave me. Pretty simple.
And in this Gantt chart, the bottom half is me, where here is learning how to use the Pixie 2 and how to get usable data out of it, and understanding what data I need and how I can receive it without receiving too much data or too little data or any other variation of that. And then I started with some gameplay here, working on as you saw earlier, the picture of calculating where a bounce shot would go or a straight shot. Then I started doing the mounting, and then I went more into the more advanced gameplay of, okay, I now know where the puck is going, I know where it'll go, how do I block it, and how do I block it well. And then this final bit here, which is probably going to start in the next week, is actually finally moving to start playing offense in our system, because right now it only plays defense, which is definitely a limitation, but the offensive implementation shouldn't be too much different than what we've done before than sending XY coordinates.
So, my basic timeline was I started out by analyzing kinematics, the equations that you saw at the beginning, analyzing the two angles in terms of the XY coordinates. Next, I built a control system for the first link of the robot, followed by assembling the robot and making a control system for the second link. Both of the control systems are exactly the same because the motors are exactly the same. So this is another video. We took this this morning at like 1 a.m. This is the first time it successfully blocked a shot. So as you can see, it's being shot and it moves the ball. So, some special thanks go out to our teachers here and a few folks who actually helped us out along the way. So, first of all, Cornwall, thank you. St. Dennis, thanks. Sam Caldwell is not here, neither is Rachel Repstead, but thanks to them as well. Rachel helped me work out how to work out the kinematics code. Sam helped him work out
all the stuff with processor editor and getting certain systics to work. And then thanks to Kevin, who does great work and helps all of us do our projects, and of course Jose.
Shout out to Jose for getting the control systems working. Yeah, thank you. Any questions?
It led to quite a few problems because, so usually when you think of a coordinate plane, you think of 0, 0 being in the center and everything goes up and to the right, and that's positive. In the Pixie, the camera, I think, let's go back. Oh no, it's just going. I may have pressed too many buttons. Yeah, so this corner up here is 0, 0, and this down here is not negative, it's still positive. So it flips the positive and negative axes, yes. And so intuitively, you think of a positive slope, you think it's going up and to the right, where a positive slope on this is actually going down. So it definitely has thrown me off, like, trying to do, I had to do most of my math, could not do it in my head, I would have to do it out on a board, and then it forced me to really double check everything, because it's just not very intuitive.
I actually have two questions. You mentioned in the beginning that the Pixie 2 can be easily trained to identify the puck.
Yes.
What do you mean by that? Like, what if we switch puck colors?
So we actually switched puck colors, I believe, 4 or 5 times. We have a little demo at our table for afterwards if you really want to see it, but it is, so say I was looking at this and the puck wasn't registering and I wanted to make a new thing, and say there's a purple piece right here, it just gives you a little drop-down menu. You highlight that little purple part at the certain colored pixels you want, and now it's looking for those, and then you can do, there's a bunch of different settings. You can how sensitive it is, how close it has to be to set color, how many of the various objects there can be of that color on the screen at once, minimum size, maximum size. So it took a lot of the hard work and gave, like the hard work of building my own image processing code and gave me basically everything I needed with sliders and stuff that is built into the Pixie.
My second question is, this week when you're working on the offense, will you be coding it so that I can play like against somebody who's at different skill levels?
At the moment, it would struggle to play against someone, like, it can go fairly fast, but if you are an avid air hockey player, this will be no problem for you. I think we're just going to try to get it to the point where it can score, and we'll go for, hopefully, a bounce shot and a straight shot.
Theoretically, if I took my control system and adjusted the game crossover frequency like I was talking about earlier, made that 100 number bigger, it would react faster. And we would be able to play a better game of air hockey against better players, but that might also break it. I'm in some of my next steps are actually attempting to improve my control system to make it respond faster.
Any more questions?
So in the control system, I think I know the answer, I'm not sure. In the control system, you don't factor into velocity. This is just going to a position and you do it so fast. That you've got the capability of using the information coming from the camera to know what the velocity is.
So we don't actually technically know the speed of, it's never calculated because we never really need to know the speed, because if we know where it's going to go, we can move to said point, and once my code sees that it's no longer going on that trajectory, it snaps right back to going home. And so yes, we could find out the speed with how fast the information is coming in, but there's no real reason to find it. It would just slow down the processing, because speed is the name of the game when trying to do air hockey. Any other questions? So a professional air hockey player, which they do exist, can shoot a puck from 60 to 80 miles per hour. And we cannot go nearly that fast. I did some calculations last night. I didn't quite have all the information because I didn't know the exact response system of some of our robot at the time. But just with the camera, I can get 2 pictures on a puck going 33 miles per hour. So I would say that's pretty good. I don't think our robot's fast enough to respond to it currently, but
How big is the code being
what was that?
How much code do you need to run this?
So I would say, how many lines do you think you have? A couple hundred? I have, I think, so it's about maybe 600, 800 lines. But a lot of my code is hidden in I use a thing called Processor Expert, which generates a lot of general code for me. So there's a lot of code that I didn't write myself, but I do use and call on. Yes. What about them? Oh, so I found that there's a lot of you'll see the little DIY robots. They usually use a gantry style where it'll be a plotter or a 3D printer where it moves around like that.
That's called a Cartesian robot.
Thank you. He's the robot guy. Yeah, so we saw a lot of that. We didn't see too much high-speed SCAR robot type machines. So this is definitely one of the fastest ones that I've actually seen working.
I think I'm trying to remember the name of the company. I think it's called Furlotech. Made an air hockey robot. They only made one of them ever, and they used higher quality object recognition camera that could go faster, so it can actually play air hockey fairly fast. It's better than our system, but it also costs a lot more to make.
Any more questions?
You all can come see our demo in green later.
Right, so, as he just said, these students are going to walk over to Green Hall, which is across the campus, and the air hockey table that you saw these videos is there, ready to play. Maybe, we'll see. But if you want to follow, that's great. I think we've got to head over there because we're grading them, so we'll be going there in a minute. But the other teams will be here, and you can continue to talk to them and ask questions and see demos. And we do really appreciate you all coming out. It's much more fun to do these things when you have a crowd and other people are asking questions. And I know a lot of you have been waiting and you've been watching these students proceed through the program. Now you get to see what they do with all the stuff you taught them and help them with. So we appreciate all of you for what you've done. And those students that are here that are going to be doing this next year, you see what you're getting into. So thank you again. Bye.
Yeah, and then but little changes of light will usually make it go off. So like if I even put my flashlight on it, it might stop tracking it. No, it's still pretty good. Yeah, no. And then so we can even track a second thing.
2 things at a time.
You can do I think up to 100 objects at a time, which. So now you're gonna want to go into the gear. You're gonna have to increase the. So then there's all these settings. You wanna to the left. You wanna decrease the inclusivity, and then it's just named yellow because I was using it for other tests. But now we can track 2 separate things. And when this is in the UART style, this pin here will be sending signals of the size of this object, where it is on the screen, how long it's been there. So the camera's super powerful and can do a lot, but we're just using it for tracking one puck, and we're going purely for XY just so we know where it's going.
Could you use the second object to track the other person's thing?
So originally that was part of the plan, but when you start tracking more than one object, it slows down how fast it can send you information by quite a bit. So we decided that it was better to maximize our time with seeing the puck and trying to play defense than trying to play a more intelligent offense.
Did you need another camera?
We could do it with another camera, or we could, there's better cameras. This camera is actually fairly cheap for what it does, and it's quite good, but there's definitely some things that it could do better.
How much did the project cost?
So
we don't really have a running total because we never really spent too much money.
yeah, like I think the most. What did we spend?
You bought a belt and carbon fiber tubes.
Yeah. So did you buy anything?
No, I got everything from Kevin.
$100.
Sounds like he owes you $50.
Oh, no, that all comes out of our lab fees.
Oh, okay.
Yeah, no, everything. The air hockey table is given to us to use by the school, so. And then, well, I guess there's all the cost of 3D printing supplies, which probably around $20-30 in there, maybe.
Is that where the Keenan air hockey table went?
Yes,
Oh.
this is the Keenan air hockey table. It is, yeah. Any other questions? you want to go talk to the other groups, we'll leave and go to we'll go to green here in a few minutes to show off the whole system. You have questions?
No. Just here to heckle.
Oh.
Yeah. How much code do you have to rewrite?
How much code did I have to rewrite? Well, that first time when I lost all my code, I only had like 200 lines, so.
When do we get to see it? When do we get to see it? Oh, I guess right now.
Oh, are we going now?
Were you going to demo?
We just demoed this. I was gonna wait.
It's at home. So theoretically, if I can manage to get this on a trajectory where it goes to the goal, it should block it.
Yeah.
Nice.
It's important for you to actually try to score, because if they program it that if the puck isn't going to score, they won't bother trying to do it.
No, it's not.
Yeah, because we don't want to move out into a position that we can't deal with.
That's why it comes to roll. Make sure it's actually.
Oh, nice. I think you just passed the offense part.
You're just trying to do a straight shot, just right at it first.
You got it. It just has to be fairly slow. Oh, we moved a little bit.
You guys are doing it for that one.
That's probably just because the camera, once you get above a certain velocity, the camera just can't grab it.
Just going easy.
All right, Josh, your turn.
Well, it just spoke up.
Let's try the other one. We totally tried this before and it won't go wrong. Oh. Well. Oh, I swear to myself. Oh. We're going.
Nice.
It can be pretty quick.
Got a double bounce.
It doesn't like the straight shot. I'm not 100% sure why currently.
Own goal Beating you so far, Josh.
Yeah, no, I keep scoring
Twice
myself.
on,
It's still making. I'm trying to get it to like sneak by. Oh, there one. It's pretty good. It just doesn't seem to like. Oh. It did it. Yeah. So that's another reason why we try not to move if it's not going in the goal, because if it's not going to go in the goal, by moving, we can knock it in ourselves, so we're minimizing risk by trying to not do that. It's not something.
I think the great thing is this legal.
If the robot reacted a little faster, it would also work better, but that's also just something that we've just recently got them to where they're talking to each other, like in the last little bit.
Let's see.
Well, I got that one.
Injured either.
Not yet.
Quickly learned by carbon fiber.
Yeah. So that's about it. If someone wants to come up and try to throw a shot and see what you can do, feel free.
Well, it's not moving.
Yeah, it knows I'm not going to make it. So it's basically saying I'm not going to move out of the position I'm at, because that's roughly the optimal place to be to defend from any angle shot. So it's not going to move out of that space to go block a shot that, say, because it's a very common strategy is to just whale it down one of the sides and have it bounce back to you to then hit it now that the person has moved out of the way. So that happens because the camera isn't like, I'm waving my hand over the thing, so sometimes it'll pick it up as being here and then here and be like, oh, I gotta move.
Wow, that's pretty good.
Yeah.
It's coming back for another.
Let's see where this is. Now, that means